Welcome back, everybody. This is the third video in a series on exponential functions. This one's entitled Logarithms. What's this? First of all, before we show you how to do logarithms, we're going to explain what's this all about. Why is there such a thing as logarithms? It's a funny word, and we're going to talk about that. So what we're going to do is we're going to take a little trip back in time to talk about this stuff. Now, when you were younger, you got problems like this, 8 times 7 equals, and then they'd put a question mark over here and ask you to find the answer. Well, 8 times 7 is 56, and we're kind of working in what you might call a forward direction. We're kind of working forward. By the way, this is called arithmetic. And this is kind of where it all starts, is our ability to do arithmetic in a forward fashion. Actually, before that, there's number sense and things like that. But now that you've gotten a little bit older, back in, I don't know, 5th, 6th, 7th grade, you started talking about leaving out this one of the numbers in the problem itself and providing you with the result or the outcome. And they're saying, okay, now we know what the answer is going to be. What would one of these numbers be? Well, for kids, this is not too bad, but this is actually working in what, kind of a backwards direction. And when we work backwards, we kind of work in reverse a little bit. It's harder for younger kids to kind of get this, how to work backwards. But this is what algebra is. Algebra is about learning how to work backwards and find the thing that's missing in the problem itself. So instead of using a question mark, we just use something like a variable. We'll just use n, and we practice working backwards through this problem. Well, you learn a whole series of steps on how to work in reverse. Most of you or all of you know that what we'd have to do is, since the variable n is multiplied times 8, we'd have to divide by 8 on both sides and get this to go out so that the variable remains, and now we can see that the answer is in fact 7. So that's the idea, is that we learn to do algebra by working backwards. But let me just make a little caveat here about this whole thing. In order to do algebra, we not only need to know how to do arithmetic in a forward fashion like multiplying, but we also need to be able to do our arithmetic quickly in a reverse direction like dividing. In addition, it's not just whole numbers we're dealing with here. We also got fractions and decimals and negative numbers and all that stuff. Our arithmetic has to be strong, because if it is not strong, then the algebra is all slowed down. We don't want to take 10 seconds to figure out what 56 divided by 8 is. We just have to be able to come up with that immediately. So the ability to do arithmetic quickly, both in the forward and backwards directions, are important. It's not just important to be able to add quickly, we got to be able to subtract quickly as well. So having said that, I just want to underscore the definite importance of having strong multiplication tables, being able to pull stuff apart, that's factoring, working with fractions, all operations, add, subtract, multiply, divide, and then negative numbers, especially subtracting and adding and subtracting negative numbers is hard for some kids. Well, this is why you can't teach algebra to students that are too young. They just, not only do they not have the ability to think backwards very well, they don't understand negative numbers and how to add and subtract those very well. It's a challenging thing to do. So we can't start too early. We kind of have to let that drop in their developmental stage. All right, let's try another problem here. This one's 3x plus 1 equals 16. Now, the more complicated the problem gets, we need to understand that we have not only got to do something backwards, we have to do it in the reverse order. Okay? In the reverse order, and when we do that, we find ourselves undoing what has been done to the variable. So let's take a look at it. Here's a variable here, and this old variable, let's put a little stick figure here. I get to draw some pictures today. This little stick figure is thinking to himself, what did you do to me? What did you do to me? And so quickly he wants it undone. What did you do to me? Well, we take x and we say, well, what was done? And according to the order of operations, the first thing that was done was multiplying, and then multiplying by 3, and then 1 was added. So if we're going to undo this, we have to undo it in the reverse order. So I'm going to subtract 1 from both sides, bring down the leftovers. These undo each other. Positive 1 and negative 1 added, they undo each other. And then the undo of multiplying by 3 is dividing by 3. So now the variable is alone, and we know that all along the variable was x. Now, this is old news for you. You've seen all these algebra problems, and you understand how to work backwards. These operations that we have been using in algebra have a special name. Well, you might be asking, why are we going over this old stuff? I don't think it's unimportant that we think about every once in a while, what is exactly we doing in algebra? Well, algebra is about getting that thing that's in the middle of equation alone so we can tell what it is. And that algebra is all about this working backwards, doing the reverse thing in the reverse order. And these operations that we're using are what are called inverses. Well, we know that adding and and subtracting are inverses, and they undo each other. Multiplying and dividing are inverses, and they undo. We know that squaring something and square rooting something are inverses, and they undo each other. Well, now we have a new operation. It's called exponential equations, or exponenting something. And that means taking something and putting the exponent up in the exponent. This exponent is up here now. It's been used to being down for so long. Well, if we want to undo this, we have to have some sort of operation that undoes exponential things. And that thing that undoes it is called logarithms. Logarithms. Logarithms undo exponential, I'm missing an N there, exponential equations, and vice versa. Exponential equations will undo logs. They undo each other. Well, what's a log look like? Well, exponentials might look like this, and a log would look like this. Log base b of y equals x. Boy, that looks strange, but we're going to learn how what everything means here and how these two work together, and they tend to undo one another. We can go from an exponential to a log and back and forth and be able to solve an equation with exponential functions. So now what the variable here is, let's draw a little picture again. What this variable now is going to say to us is, you know, how did I get up here? How did I get way up here in an exponent? I'm kind of scared of heights. You got to get me down. I don't know how to get down, and we need to teach you using logarithms how to pull this down so that we can actually say what x is equal to. It doesn't stand to understand it up there. So it's kind of standing up on this platform up here we call exponents, and it's looking down at everything else. Up until now, we've always kind of stood at the bottom and looked up at things. But here, how are we going to get this guy down so it makes some sense? So, in conclusion, a logarithm is the inverse. Logs are the inverse of exponentials, and vice versa. They're the inverses of each other, and they're a way to rescue x from its prison up there, as we want to call it, its prison of being up in the exponent, that lofty spot it has up there. We're going to rescue it from that, but we're going to use logarithms to do that. Now, it's pretty important, this what I just explained to you here in the last 8 minutes or so. If you need to, go back and watch it again, because it explains completely why we do algebra and why logarithms are needed. All right, so let's get into the nitty-gritty of what logarithms are. This operation called logarithms is the undo operation for exponentials. So if logs are an undo operation for exponentials, then they're going to help us to get x down out of the exponent and bring it down. Here's another phrase that you might want to hang on to. Logarithms, I'll just abbreviate using the word logs here. Logs are exponents. Logs are just exponents. And if we try to remember that, logs are exponents and exponents are logs. They're the same thing. It might help a little bit to understand how to work with these. Now, you might see something that looks like this. Log base 5 of 25. Now, let's put a question mark over here, although I'm going to start using the letter Y or N in a minute. What is this statement saying? It's asking a question, and that question is, what is the exponent? See, logs are exponents. What is the exponent on a base of 5 that will produce me a number of 25? Well, that's saying if the number is 25, what is the exponent? What is the exponent on 5 that will produce 25? Let's talk about it another way. And let's just put letters here. Log base b of y equals x. And what we're going to do is we're going to give these some names. This we know is called the base. And as you recall, the base has some restrictions. The base cannot be, the base is greater than 1, and the base cannot be 1. There's some restrictions on the base. This thing x is an exponent. Remember, exponents are logs. So if this is an exponent and it's equal to a log, they are exponents. It's an exponent, and exponents are logs. And this thing we're going to give a name, and we're going to call it the result. Some teachers just call this the number, but I call this the result. And the reason for that is we take the result, and it is equal to the base raised to that exponent. Get used to this pattern, because this rhythm that we're going to need to follow is to be able to put everything where it belongs from problem to problem. So the first part of your assignment is going to be to translate logs to exponents and exponents to logs. Let's say it again. This is a base, this is the result, and this is the exponent. And the way we say this out loud is log base b of y is x. Log base b of y is x. Well, let's try a couple problems. All right, let's start with this one. And we would say this, log base 8 of 1 is 0. Again, this is asking, what is the exponent on 8 that will give me a result of 1? Well, we're going to go ahead and just transfer this. The instructions in your book will say something like, turn this into exponential form. Okay, so we're going to do it, and we need to pull the result straight down. It's important that it goes straight down, because we get to inequalities. It has to be on the correct side. Pull the result straight down, throw the base to the other side, and apply the exponent. There it is. Well, we know this is true. Anything to the 0 power is 1. Let's try this next one. Again, this is asking the question, what is the exponent on 2 that produces a result of 1/16? And they're telling us that it's negative 4. Well, let's pull the result straight down, throw the base to the other side, and apply the exponent. Now, is this true? Well, it is, because 2 to the negative 4 power is the same as 1 over 2 to the 4th, and we know 2 to the 4th power is 16, so that's true. Okay. All right, let's take this one. This is asking the question, what is the exponent on 3 that produces a result of 9? Well, bring the result straight down. We're going to call that result. Throw the base to the other side and put the exponent up. You notice when the base is over here, it's tiny, and when it's over here, it's big. That's vice versa. Here, when the exponent is big over here and it gets tiny, that's because this is exponent world, okay? And in the exponent world, the exponent kind of is dominant, okay? Here, this is in the logarithmic world, excuse me. In an exponent world, the base is kind of dominant there. Well, we know that's true. Let's try another one here. And let's try to go the other way. Let's say we want to turn something that's in exponential form and turn it back to logarithm form. Well, what's what here? Well, there's the base, there's the exponent, and there's our result. So we would write it, let's go back over here, we would write it log base 10 of 1,000 equals 3. Let's do another one here. How about 9 to the 1/2 equals 3. That's an exponent there. Maybe I need to make it a little smaller. It's a good lesson for all of us that you don't let those creep down or they look like they're part of the number. Well, there's your base, exponent, and result. So let's go back over here, go this way. We'll write log base what? Well, the base is 9, the result is 3, and the exponent is 1/2. What's the log? What is the exponent on 9 that produces 3? Well, the exponent was 1/2. Here's another one. 27 to the 1/3 equals 3. Okay, well, let's do it again. Log, the base is 27, the result was 3, and the exponent is 1/3. What is the exponent on 27 that produces 3? Well, it's 1/3. Now, what you realize we're doing here is we're actually searching for exponents, then instead of just searching for the answer to something raised to an exponent. All right, part of your instructions on your homework tonight is going to ask you to do what's called evaluate. It's just a fancy word for saying what's its value, what's it equal to. So you're going to get something like this, log base 2 of 64. Use the word of here. And they're not going to give you an equal sign here, but it really helps if we take the initiative to put a variable over here. Anything. I'm going to use n, and we're going to rewrite this, if necessary, in exponential form so that we can make sense of it. All right, so we'll bring the result straight down. The base is 2, and we're raising that to the n power. Now, like we did in the last video, we talked about smell a base. I smell that 64 has a base of 2, so I'm going to rewrite this. 2 is 2 to the what? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. Well, that was 6 of those. So we can see that the exponent here, n, has got to be equal to 6. N must be equal to 6. If the bases are the same, then the exponents would also have to be equal. Let's try another one. How about log base 3 of 1/9? Okay. Again, we're going to initiate by putting an equal sign here and a letter, just to stand for something for now. And we're going to rewrite this in exponential form. So 1/9, bring it down, equals the base raised to the nth power. Okay. So what do? Well, I smell a base here. I smell that this is the base 3. This is 1 over 3 squared. Now, they don't exactly have the same base yet, but we can turn this upside down and call it 3 to the negative 2. Remember, we flip it over. We can turn this upside down and put the base up on top here, and now we can see that the answer here, negative 2, has to be n. So as you go to do your homework, you need to think about how to just develop that pattern, that rhythm that knows where everything's supposed to go, and it'll all make sense as you can start to transfer. Well, here's where the base is, and here's where the exponent goes, and here's where the result goes. That's only 3 things you're going to have to worry about: bases, exponents, and results. Now, there are some situations that deserve our special attention. I'm going to call them special logs here. Here's one of them. Now, sometimes we get situations like this and we wonder, well, what's really going on here? Well, let's see what happens here. Drag the result down, throw the base to the other side, and apply the exponent. And we go, oh, that means 8 to the 0 power is 1. Well, that's always true anytime you raise something to the 0 power. So if there's a 1 right here in the result position, no matter what the base is, just like no matter what the base is here, anything to the 0 power is 1, no matter what this base is, if there's a 1 in this position, it's equal to 0. That's always going to happen. Okay, here's another situation. Well, let's see what happens. Notice these two numbers are the same. Well, let's put a letter in here and see what happens. Drag the result down. I'm bringing this number down here. I'm throwing the base to the other side, and I'm applying the exponent. So this is 6 equals 6 to the n. Well, what is that number right there that you don't see? Well, of course, it's a 1. So that means n is equal to 1. So it's telling us log base 6 of 6 is 1. In other words, if this base and the result are the same, that means that it's got to be equal to 1. Now, this is really important because what it's telling us is that a log base and a base, in this case it's a result here, but a log base and this result, they always undo one another. A log base and what we call a base always undo each other, and they give us 1. This is the undo operation that we'll be spending a lot of energy thinking about. The fact that a log base and a base, when they are the same, it ends up being equal to 1. Let's try another one here. This is sort of a version of the last one we did there. All right, let's go ahead and take this one. We're going to drag the result down. Notice this time the result's coming down and it's bringing an exponent with it. In fact, sometimes you're going to bring stuff down that brings lots of different things with it. Just bring it down with it. Throw the base to the other side, and then we don't know the exponent. Let's put n there. And now it's obvious to see that because the bases are the same, that n is equal to 8. Well, this is also an important characteristic of this. If the log base and the base of this particular result are the same, then the answer is simply the exponent. Remember, we're looking for exponents. This is saying, what's the exponent on 6? That will give me 6 to the 8th. Well, that's obvious. The exponent on 6 that will give me 6 to the 8 is 8. That makes perfect sense. So when you see this particular pattern, you're going to go, oh, it's got to be 8. Well, the same thing was true over here. Notice there was a 1 up here, you just never saw it. What is the log base 6 of 6 to the first? What is the exponent on 6 that gives me 6 to the first? Well, it's 1. That situation is prime real estate for us as we're working through. All right, this next problem is a little different, and it's one of those that I kind of hate using this particular approach when I'm doing my logarithms, but it will come up every once in a while. I just want to make you aware of it. Notice that this problem is actually written in exponential form. Even though there's a log in it, there's the base and an exponent. This whole thing up here is an exponent. So I'm going to put a letter n here, and we're going to turn this into exponential form, logarithmic form. So I want the log base 3 of the result. There's the result. Log base 3 of the result equals, this is my base right here, right? There's my base. Log base 3 of the result is the exponent. Well, in this case, the exponent is this. That's right here. This whole thing is right here. This whole thing right here. Came down here. Log base, this is a base. It's coming down here and becoming a base. Log base 3 of the result, there's our result, is equal to the exponent. Well, if you look at these two, log base 3 on both sides, that stands to reason that these results here inside n and 4x minus 1 are the same. Now let me write the problem over again so you can see without all this writing. What it's saying is, let's put this up here again. If you have a problem where the base and the log base are the same, then the answer is simply that thing that's up here with the other two, the result here. So these two, again, undo each other. In the previous problem, they look the other way, where they look like this. Log base 3 of 3. These are undo operations, and these are undo. These are both undo operations. Here's the one where the base is 3 and the log is the exponent. here's where the log base and the result are opposite. So they're the same and they undo each other, and the answer to this is just whatever happens to be up there in the exponent right there. So, so these are some special situations that may come up, and they'll come up all the time, but just to make you aware. If you need to come back and look at this sometime, please do. It's all right. You have enough information now to do the next assignment. This next assignment is assignment number D, and it's page 535, 3 through 11, and 21 to 32. I'm going to put another video up today that's going to allow you to do assignment E and maybe F as well. We'll see. And you're ready to do this assignment in the book. I'm going to go ahead and do a couple problems with you. I'm going to let you do number 3 on your own, but let's take a look at number 4. The instructions for number 4 say, write each equation in logarithmic form. Okay, so we're going to just practice now that habit of moving things where they go. All right. Log, well, what's the base? The base is 5. What's the result? Well, it's over here. And what's the exponent? It's 4. That's all you have to do is write it so that it's in logarithmic form. Let's do another one. How about number 5? Okay. All right, here we go. Log, well, what's the base? The base is this 7. The result is 1/49th, and the exponent is -2. No big deal, just go ahead and put everything where it belongs. Now, problem 6, the instructions say to go the other way, so they're going to give us a log this time and ask us to turn it into exponential form. So what's key here is remember to bring this result straight down, throw the base to the other side, and apply the exponent. That's all you have to do. Okay, I'll let you do number 7 on your own there. All right, let's do number 8 together here. The instructions are changing here. They're using that word evaluate. Evaluate. Now that's telling people, okay, basically, what is this equal to? What's the value of this? Well, this is a little harder to do without an equal sign, so we're going to just introduce one here, and we're going to call it n. There's the thing we want to find. So when we evaluate, n will be our evaluation, will be the answer. So in order to do this, let's turn this into exponential form. Drag the result straight down, throw the base to the other side, and apply the exponent. Now here's where we're going to smell a base again. Well, 256, if I think back on all of my numbers, I know that 256, 4 times 4 times 4 times 4, or 16 times 16, happens to be 256. So it's going to give me the same base, so this is 4 to the 4th equals 4 to the n. Well, since the bases are the same, n has got to be equal to 4. Number 9. I'm sorry, let's do number 11 instead. Once you do 9, 10, you're on your own there. Let's take a look at number 11. Log base 5 of 5 to the -1. Okay, well, remember that principle we talked about where the log base and the base are the same? This base of this exponent are the same? Well, let's just go ahead and prove that. Let's put a letter out here. Let's drag down the result with anything that comes with it. In this case, the -1's coming with it. Throw the base here to the other side. We drag this down, all right, and then apply the exponent. Well, we can see obviously that n is equal to a -1. So you can see from this that this would be a shortcut, would be to notice that those two undo one another. And this is an important concept to kind of get logged in your brain there. So go ahead and finish assignment D, and I will put up the next video here on how to solve logarithms. Have a good one.